Okay. So our goal is to be able to say what is what I called CK of J, which is the coset of the Westominov-Witten theory at level k minus 1 times the 1 at level 1, and it's the diagonal coset. And similarly, with a lower label, this is just to say that there are actually two problems to look at. If I look at the simple quotients. So Vk denotes the Westominov-Witten theory if I don't quotient by any null vectors at all, and L if I set all null vectors to 0, so that I'm looking at the simple quotient. It's interesting to look at both of them. And and the answer will turn out to be a W-algebra, a quantum Hamiltonian reduction. So this means last lecture I had to explain to you what a quantum Hamiltonian reduction is. And what we did there is we defined the W-algebra of a Lie algebra at level k corresponding to rho, where rho was an embedding of SL2 in our Lie algebra. This embedding gave us a decomposition of G of the Lie algebra into SL2 weight spaces. And this weight space decomposition told us that if we now take the Westominov-Witten theory, the vertex algebra of G at level k, together with a free field algebra, which I now just call ghosts, this decomposition told us that in this big VUA, there is a differential D, which I called standard differential plus character, where the standard differential was of the form a pairing of the currents of the Lie algebra with the corresponding ghosts, and the sum went over only the positive graded part of the Lie algebra, only the positive weights of SL2, plus a cubic term in the ghosts. And the character, in the simplest case, it's just a single ghost. And maybe it has. And then this W-algebra, the most important property is that the zero mode of this field has the property that it squares to 0. So it has the property that it can be a BRST operator. And so especially the image of this operator is in the kernel. And so it makes sense to look at the quotient. And the W-algebra is then defined, that's the definition, as the cohomology of D naught. So this means it's the kernel, and we identify fields that only differ by fields in the image. So this is the formal definition, and it sits kind of on the top. So in principle, what you always want to do is you have a few basic constructions of vertex algebras. We also talked about the coset construction and the orbifold construction. Each construction has its benefits, though the coset one is really the nicest one. And but you understand most if you are able to realize your VUA in each language. This is at least my take on this. So this means, let me maybe first give an example before I continue. And the example here is the most famous one. So we take for G SLN, and we take the embedding, which is called the regular embedding. So it maps the element E of SL2 to the n by n matrix, where we have zeros on the diagonal and ones just above the diagonal and everywhere else zeros. It maps F to the transpose of this matrix. So so just ones right below the diagonal, and H is mapped to 1/2, and then here it's mapped to a diagonal matrix where the diagonal entries go from n-1 to 1 minus n. And this one is called, so this is called the regular embedding. Of SL2 in SLN. And so this W-algebra is called the regular W-algebra. In the literature, it will often be said to be the W-algebra of SLN, but as we saw, there are also other ones. Now, if one has this decomposition, a first thing one would ask is, how does SLN decompose in terms of modules for SL2? And it turns out it decomposes into 3-dimensional representation plus the 5-dimensional plus the 7-dimensional and so on up to the 2n minus 1-dimensional representation. And one thing that quantum Hamiltonian reduction gives you for free is then the type of W-algebra you get, because for each irreducible SL2 representation appearing in G, you have precisely one strong generator corresponding to the lowest weight vector of this representation. And the conformal weight of this one is given by, so the conformal weight of the field corresponding to the m-dimensional representation, let me just, is m plus 1 over 2. And so this means if we look at this, we see we get a W-algebra of type 3 plus 1 over 2, 5 plus 1 over 2, and so on up to 2n minus 1 plus 1 over 2. So we get a W-algebra of type 2, 3, up to n, which is, and recall what this means is, this W-algebra has one field in dimension 2, 3, and up to n, so that every other field in this algebra can be written as a normally ordered polynomial in these n minus 1 fields together with their derivatives, iterated derivatives of these fields. So this is the structure. And now I would like to, the aim of this lecture is to give you an idea why these cosets are W-algebras of this type. So, so let me maybe first sketch the idea. The idea is the following, and this is a fairly general idea. So you start with some free field algebra. Free field algebra, so this means I mean a vertex algebra that's composed just of a few free bosons, maybe symplectic fermions, maybe a few ghosts, fermionic or bosonic ones. And then you would like to be able to embed your interesting algebra, your interesting conformal field theory in there. So you have, so you can just restrict to the sub-algebra. And this is then usually called a free field realization of this interesting algebra. And this restriction map is usually, you can realize this in what is called as the kernel of screening charges. So at the end of last lecture, I presented such a screening charge, and I will recall the end of last lecture in in 10 minutes or 15 minutes. But now what you want to do is you want to understand a certain cohomology of the VOA. So this then just goes to the, let's call it HD of the cohomology of this VOA. And but since this we have an embedding of our VOA in a bigger, much easier VOA, of course our differential embeds here, and so we can also take the cohomology here. And then we can take a restriction here. And the idea is that these operations commute. So that, that we have something we want to understand, namely this arrow. And what we do is we push it up one level where everything becomes extremely explicit, and that means much nicer. And then the art is to understand that indeed one can go the other way around. So this is the idea. And now let me first write down the theorem. So this was an open conjecture since the 80s. And everything can go, yes. And this has been proven by Arakawa, Tomiyuki Arakawa, myself, and Andrew Linshaw, beginning of last year. And it says that let K be generic. Well, maybe first let G be simply laced. This means G is of type SLN, SO2N, or of type E. And let K be a complex number, and define, and L defined by a very nice relation, which I can explain in the tutorial more if you like what it means, because it has a nice meaning. So H check is the dual Coxeter number, which we have seen already in the Westermino-Witten lectures. And so the relation is that the sum of the inverses of the shifted levels add up to 1. So it's a condition that might look like a surprise, but it is a very natural relation. So then if these are, oh, maybe you can leave this here, please. Yeah, but I'll use it. And then the statement of this theorem is, so I continue here with the theorem, and then for K generic, and generic means really any complex number except for certain negative rational numbers. This one is isomorphic to the W-algebra of G at level L for the regular embedding. And I just represented in the example the regular embedding for SLN. There's also a notion of a regular embedding for SO2N and type E. And the statement is this coset is just such a VUA, and here in this case, and here for K admissible. So I'll say in a moment what admissible means. We have the same type of isomorphism. The lower index means it's the simple quotient. It's the simple W-algebra. Here it means the universal. This means same thing as here. I quotient by no null vectors at all. Here I quotient by all of them. That's the difference between the two. So it turns out, if one looks at the Westermino-Witten theories, you learned if K is the level is a positive integer, you have many null vectors, you can quotient by them, and then you get a very nice conformal field theory. What a conformal field theory that's called a rational conformal field theory, because representation category is completely reducible. It's actually even a modular tensor category. And it turns out if the level has the property that the level plus the dual Coxeter number is a positive rational number, except for a few cases on the boundary, then again the universal affine vertex algebra has many interesting null vectors. You can all quotient by them. Quotienting by them, passing to the simple quotient restricts the spectrum of the theory substantially, and in those cases it nonetheless you will still have infinitely many modules. Modules will not be completely reducible, so one would call it a logarithmic theory, but you get still quite interesting theories, and especially the W-algebra of it. is a rational conformal field theory. So, these levels are the ones one is usually interested in. And so this means really the most interesting part of this theorem is here the second statement. Not the critical level, no. It's just it has to be positive, and then I mean you take a few levels away, which I don't write down. Essentially, so you write k plus h check as a positive rational number, and the numerator has to be at least the dual Coxeter number for this to be an admissible level. That's the condition here. Okay. So, actually this theorem can be upgraded further. So this is and this will appear soon. Well, I don't know whether it appears soon, but we have the proof written down. So it should appear this year. So now we define, let me only do it for the universal one. For the simple quotient, there will be a similar statement. Now I define a new coset. I call it CK with a subindex rho, where rho is an embedding of SL2 and G, and G is simply laced, so of type SL, SO2N, or E. Then I replace here in the numerator my affine VOA by the W-algebra. I still tensor with the lattice VOA, but I should write here maybe an index rho twisted. And then in the first case, this is completely non-obvious. It turns out the W-algebra, where the level is shifted by 1, acts on this big theory. And so you can take the coset, and this coset is isomorphic to the W-algebra of G for the regular W-algebra. So this is a huge upgrade of this theorem. So it's kind of interesting. The regular, so you have on the top your affine VOA, then you have kind of the nicest, the regular embedding, and all intermediate W-algebras you still can realize in terms, they are involved in a coset realization where the commuting partner is just the regular W-algebra. And
so the condition on rho is just that it's an embedding,
any. So it works for any. This means, and you know you have many embeddings. You have a question?
What is a superscript on the L1 G?
It's all right, and I forgot this. So if you now compute central charges, you'll see central charges don't match. It's a bad sign usually. But this one just has a Heisenberg, a free boson in there, and you can always change your free boson. You can change your Virasoro field by a derivative of this free boson, which means you essentially have a whole one-parameter family of possible Virasoro fields, and the Virasoro field of these two subalgebras. For this, you need not the standard one, but one twist, and I just call it O twisted for saying that you don't take the standard Virasoro field. So for this discussion, this is just a subtlety that is maybe not so important here. Okay, and this theorem has a corollary that is rather powerful, and because of this corollary, I mainly wanted to discuss the space change business, because so now we have our quantum Hamiltonian reduction, meaning we take the cohomology for the embedding rho, and this maps a module. Let's call it in general Vk of lambda. So by this I mean the module of the affine vertex algebra that has highest weight lambda. So just a highest weight module for the affine D algebra. then this maps it to the corresponding W-algebra module, which I just call like this. So this map lifts to a braided monoidal equivalence of vertex tensor categories. Oh, and here actually I want to talk about the simple quotients. I'm sorry. Lifts to a braided monoidal equivalence of what is called vertex tensor categories. And if they exist. So in the very first lecture, I mentioned that the main problem is the existence problem. So, but for a few cases, we have handled it. For example, for if if the level is admissible, then E.G. Huang, Jinwei Yang, and myself, we have proven this existence statement. And for the regular W-algebras, it has been known for a long time. It's a theorem by Arakawa again. So it lifts to a braided monoidal equivalence. And now, thanks to Niels, we can appreciate this statement. He has explained to us what monoidal functor is, what braiding is. And I hope you can appreciate this statement because it means, for example, if I know fusion rules here, I know them immediately here. And if you want to take it on a more physics level, one can also rephrase it. There are equalities of correlation functions. So you would say maybe you get a correspondence between certain special correlation functions. That's a more hands-on statement, maybe. This corollary you can actually prove by yourself if you know the fusion rules of the W-algebra and if you know actually what is the decomposition in terms of the big VUA in terms of the coset modules. All this information I give in my lecture note, I just don't have the time to write it down. Also, I didn't explain the notation. But this would be a possible exercise for this afternoon, that we discuss why something like this is happening. So don't be scared. We can do it in SL2. We can do it in a very explicit setting. But I think it's this shows you, I think, what a benefit of such a theorem is. In any case, and now, okay, anyway, this is the important theorem. Now we look upstairs at the idea, and so that because now I want you to get a feeling why this theorem is true. So we now take G to be SL2, and now I will do twice something very similar, at least if I have enough time. And both times I use this idea upstairs to explain you how to explain you this coset theorem, and in general how W-algebras are related to free field algebras. So yeah. So for SL2, the first thing one has to know is that there exists a Wakimoto, what's called a Wakimoto free field realization. This means as free field algebra, one takes a free boson and a system of beta gamma ghosts. So the free boson has just OPE with itself to be 1, second times the second order pole, and beta gamma this OPE. Can you already? Thanks. And then it turns out that in this free field algebra, if you define the fields E of z to be beta, H of z to be, I think, square root of kappa times x, minus 2 times the normal ordered product of beta and gamma, and then f to be a cubic term in beta and gamma, here I defined kappa to be the level plus the dual Coxeter number. And then it turns out that one can, this is a computation, that's probably a good exercise actually, that the OPEs of these three fields are precisely the OPEs of SL2 at level k. And so one says this gives a free field realization of SL2 at level k inside this free field algebra of a free boson and a system of beta gammas. And now one wants to characterize this precisely, and the statement is that the affine vertex algebra, so our Westomin-Witten theory of SL2 at level k, is what is called the kernel of a screening charge on this free field algebra. And this screening charge is the zero mode of an intertwiner, and it's the intertwiner is it is written like this, and in order to understand it, one has to talk a little bit more about representation theory of free bosons. So let me just say it is. And this one is the primary, is the notation for the primary field for the highest weight representation of the Heisenberg of the free boson algebra, where the highest weight is minus 1 over square root of kappa. So, and it turns out the zero mode acts nicely on the affine VOA, and it's on the free field algebra, and the kernel is precisely the affine VOA. So I had already sketched that very quickly at the end of last lecture. And this S stands for screening charge. Okay. And now, we want to take this idea here and try to understand whether we can use this screening picture to also realize the W-algebra of SL2, which is just the Virasoro algebra, in terms of screening. Okay. So first, we recall that in the case of SL2, our differential is just the zero mode of this simple field. And now, and this is so simple that we can nicely compute the action of D0 on basic fields. So for example, now first of all, I insert my free field realization, and we see that the field E is just beta. This is, of course, extremely convenient, because now I can compute the OPE of D with the ghost field C. So here I introduced a pair of ghosts with OPE with this OPE as presented in the very first lecture. And from this OPE implies that the action of the zero mode of this D, that means the action of our differential on C, replaces just the B by a 1, so we get beta plus 1. So this means beta is in the same cohomology class as the number -1. Beta is just a constant in cohomology. Similarly, we can compute the, how the D0 acts on gamma, OPE of beta and gamma. Where do we have it? Here. Beta and gamma gives us also a 1, so this will just give us the B. So we see that means B is in the image, so it's trivial in cohomology. But on the other hand, X does not appear here, and B and beta commute with X, so this means our Heisenberg field remains non-trivial in cohomology. Our cohomology still contains the Heisenberg algebra, and actually turns out that the cohomology of our big free field algebra, namely the ghosts times the free boson, is just the free boson. So so this means, if I write this suggestively, we have here our VUA given by gamma, by the free boson and beta gamma, and the cohomology is just a single free boson generated by X. Now, our restriction is taking the kernel of our screening operator, and it gives us the affine VUA. And remember, I want to understand the cohomology. I want to understand the W-algebra. I want to understand SL2. So now what I just do is I take here the kernel of the class of the screening charge. This means the class of the screening charge in cohomology. So what do? But now look at the screening charge. It's beta times something in X, something in the free boson. Free boson commutes with the differential. But beta is cohomologous to 1 if and the pre-image is the ghost C. So what do? I take now again the action of my differential, but now not on C, but on C times this exponential. Because if I do this, what do I get? I get this differential times beta, this exponential times beta plus 1 times this exponential. So I get the Wessomino-Witten screening charge plus this exponential. And so let me just call this the screening charge of Virasoro, of the W-algebra. So I have understood that so I have found a free field realization of the Virasoro algebra, and this is a very well-known free field realization of Virasoro, and you see, you can very nicely see it from this idea, right? This is the point I wanted to make. Right? We have difficulties with cohomology, especially if we have some abstract, some complicated-looking VUA. But if we can move it up, if we can embed it in something we can control very well, namely a free field algebra, then we can do our computations on the level of the free field algebra, which you see are quite doable, and then push everything down to our problem of interest. And this is precisely the way how we got the idea how to prove the coset theorem. And so I will now explain in the remaining minutes that I have the key idea how to prove the coset theorem. It's almost the same.
So that's for simple case, or because examples were too.
Right. The type B also works in this way. So this is SL2. If I take SO2n plus 1, SO odd, then the whole proof goes through in a very similar way. And then actually the whole proof idea goes through in a huge generality, and you will always end up with a description of your coset as kernel of certain screenings. The question is then, can you identify these certain screenings with something known? if you do this whole procedure for type B, for SO2n plus 1, then it turns out you get the screenings of the regular W superalgebra of OSP1/2n. So you get a superalgebra. But also what you have to do is you have to replace the L1G by free fermions, because SO2n plus 1 lives naturally in 2n plus 1 free fermions, which we actually learned in the Westermino-Witten lectures. Okay? So there it works also well, and I have the suspicion that it works in so many nice cases, but it's getting more and more difficult. So this is the easiest case. Okay. So we repeat this now, but I first have to tell you a little bit about SL2 at level 1, because it also has a very nice free field realization, namely in terms of exponentials of free boson vertex operators. Where here Y is a free boson with OPE same as X. I'm sorry, I think if you cannot read this, it's precisely the same VUA as X. So I just take a second free boson. And so now I want to do something similar. Can you please erase one more board? I want to do something very similar, so the same type of idea, and but what turns and now I will use the Wakimoto free field realization, and all I do is here I change my differential a little bit. I take the standard semi-infinitely algebra cohomology on the diagonal SL2 algebra. So I take the differential B times my E plus my E1. So this is now inside Vk minus 1 SL2 times L1 SL2. So now I want to look at the same type of commutative diagram as above, as there, just that I take now a different cohomology on a different VUA. And the upshot will be same type of computation goes through, and it's just that on the and we again precisely get the Virasoro screening charge as an answer. So let's try to see this. So the commutative diagram we want to look at is we have here on the top the Wakimoto free field algebra. We now take it as at level k minus 1, just because I like to write the k in the denominator. And right, this is. So now we want to take the cohomology here again, but here we can go down to our affine VUA and take here the cohomology, and here we get something, and here we can identify the coset. Let me write it so suggestively, and I don't have so much time, so I will at least want you to present to you how this. Yeah, the whole proof idea is very, very general. That's the main point of it. I mean, this is a new idea that allows you to understand very nicely how to relate quantum Hamiltonian reductions to cosets. And yeah, that's the point. You always have, I mean, that's the difficult thing that I'd go over. You always have to show that these diagrams commute. I mean, so first you do this computation. That's kind of the key observation, namely what does the screening charge become in cohomology. And then you have to carefully understand that this diagram is indeed commutative, which is a whole different question. Sorry. So here we have our standard, and now here we do precisely the same computation as here. We look now at the zero mode of it, acting on C times, and of course I insert here my free field realization again. So this is just the field beta, and I apply it to the corresponding exponential. So you see, even the computation is precisely the same. And if I compute this, the action of D0, I again get beta times this exponential plus now E1 times this exponential. So I get, the first term is just the screening charge of the Westomin-Witten theory. And the other term is now the exponential of the field y of z, which is just my E1 here, and minus the one of minus this term. And now you call this, you take this diagonal free boson, you call it maybe Z, say. You rescale it such that it has norm 1. So that means you would define, you now define a Z. So so let's call this our next screening charge, just S. And what we did do is now we define Z to be X minus square root of K minus 1 Y divided by square root of K. So this dividing by square root of K ensures that Z has norm 1. And so then, and then it turns out S, you can just do it for yourself, is now with this new variable, the screening charge is of this form. And this is precisely the screening charge of the Virasoro algebra at level L, where L is defined is not defined anymore. That is my fault. So this is precisely, this is Virasoro at the dual level L. And on the other hand, you can also, now what else do we have to do? This one we can nicely decompose. Here, this is a free field algebra. Doing a coset decomposition in a free field algebra is a problem that you essentially get for free. So here you can decompose it, whatever is the pre-image under this restriction of the VK minus, under the diagonal VK SL2, and then the multiplicities. The cohomology does not act on the multiplicities, so the multiplicities stay the same, and it turns out this one only acts on the multiplicity space, which is then which then proves the theorem, provided you can show that the corresponding diagram indeed commutes, which is of course then a lot of tedious work. But I hope you get the idea, and I hope you, from this, you appreciate that it's also good to have for me really the semi-infinite cohomology, the quantum Hamiltonian reduction, sits on the top, and then you can go to nice concrete pictures via certain methods, and really the methods I presented. So then and then you have either your free field realization in terms of kernels of screenings on a free field algebra, or you have your coset realization. And then really understanding them I think, is understanding all three concepts, or from each concept you get something interesting. And for example, so I got a little bit drawn to questions in higher dimensional physics, and this corollary is absolutely essential here. For example, what one wants to do, well, maybe I can explain that more in the tutorial, but one wants to do something similar as Niels presents it, maybe not with Riemann surfaces, but with higher dimensional manifolds. But still you want to do a kind of TFT construction for them. And it turns out it's useful if you label higher dimensional structures by vertex algebras and their categories, and then you can glue your higher dimensional structures, and you can glue them only if, the boundaries on which you glue are labeled by categories, and you can only glue if the boundaries are the same, which translates to that the category are braid reversed monoidal equivalent. So this corollary actually is telling a lot also in perspective of what Niels is doing. Okay, so I hope that you got out of this lectures that there exist various constructions. And that was the main part. And if you come to the tutorial, we can actually do whatever you like. So I will ask what the majority wants to do. But something very nice is to try to understand this corollary a little bit better. We can do it in the case of SE2. We can do it in generality. It's as you like. So thank you very much for your attention. Yes.
Okay. What is the necessary condition for you to be always able to identify your screening charge? What is the necessary condition for you to be always to identify your screening charge? What is your screening charge?
So the question is, what's the condition that I can always identify the...
The B action is enough? Is the B action enough, or there is something else?
Yeah. So essentially the question is, how does one generalize this? Because one has there are so many cosets that we all expect to be nice W-algebras, and we don't know. And so so from this perspective, it relates to what are the conditions on the screening charge that I can do such an identification. And essentially, it is whenever I can write the coset, the numerator theory of the coset in terms of an affine vertex algebra, a VKG, and a free field algebra. So for example, for string theories, the most interesting cosets are maybe the Kasama-Suzuki ones. There are, you take SLN plus 1 at some level, you take free fermions which carry an action of SLN at level 1, and then you have a diagonal coset by by the SLN at level k plus 1. So, and it turns out this coset has n equals 2 superconformal symmetry. It's, and the big conjecture is that whether it's a regular W superalgebra of the Lie superalgebra SLN/n plus 1. And for that one, this method also applies. So this is what you are interested in. So, yeah. But then there are further cosets for which it at least not yet does apply. So I'm interested, yeah. Anybody, you had one?
It was really it.
Okay.
So this corollary you had, that of course relates to the relation between the fusion rules. You said also qualities of correlation functions which would be stronger. Because it would also really structure constants, but then it would
yeah.
field constant, not just
I'm happy to explain that statement more precisely in the tutorial. The way I view it is, so I should have written of certain correlation functions, and the certain makes it equally strong. Yeah.
Okay. Are there no more questions? Then, well, thank you very much again for your lectures on W-algebra.